So the first example I want to look at is we want to derive a power series for f of x equals natural log x centered at 1. Man, make that just a little bit more legible, but centered at, we'll say x equals 1. So we're going to go through the process we did yesterday because natural log x isn't in the form a over 1 minus r. The derivative you might be able to manipulate to get in that form actually, but we're going to do this using what we did yesterday. So what we said yesterday is that the form for the power series, so if we've got natural log x, if we've got a series that's equal to that, it would be the sum k equals 0 to infinity fk of the center being 1 over k factorial times x minus the center to the k, so x minus 1 to the k. And the idea is that we plug in 0, 1, 2, 3, and so on for k, and the only really complicated part of this is the top, because that's the kth derivative evaluated at 1. So to deal with this, we make a list of the function and several of its derivatives until there's a clear pattern. So f0 of x is just f of x, that's natural log x. Obviously, the first derivative then is 1 over x, and we don't need to think of it as x to the negative 1, but it makes it easier for the derivative if we do that. So the second derivative, if we think of it as the power rule, is negative 1 x to the negative 2, but when we write that, we probably should write it as negative 1 over x squared. The third derivative is the derivative of that, which is then positive 2 x to the negative 3. And so we want to rewrite that as 2 over x to the third power. And then the fourth derivative, you bring the negative 3 down, and we're going to write this as negative 3 times 2 x to the negative 4. And the reason we're going to do that, so obviously it's negative 6, but the reason we do that is because if we bring the 3 down, this is 3 factorial, and if we bring the 4 down, on the next one, it's going to be 4 factorial because it's 4 times 3 times 2 times 1. And so we want to leave that in the expanded form so that it's easier to notice that it's a factorial. And so then if we do one more derivative, so let's say let's do f5, so fifth derivative of x, that's positive 4 times, whoops, do that in red just to be consistent, positive 4 times 3 times 2 times 1 times x to the negative 5th. And so then we can write that as 4 times 3 times 2 over x to the 5th power. Okay, so to do this process, we make a list of the function and a bunch of its derivatives until there's a fairly clear pattern. So as we keep going, these become higher and higher factorials, and they also alternate negative, positive, negative, positive. We're then going to plug in the center for all of these. So we're going to do f of 1, and then f prime of 1, and f double prime of 1, and so on. And so if we do that, then the x part just becomes 1 to whatever power. And so basically goes away. On the first one, we get natural log of 1, which is 0. But then we get 1 over 1, which is 1. Negative 1 over 1, which is negative 1. 2 over 1, which is 2. Negative 3 times 2 over 1, which is just negative 3 times 2. And then 4 times 3 times 2 over 1 to the 5th, which is just 4 times 3 times 2. Any questions to here? I know this is like a weird process. We did it with sine. Yes, I think we did cosine centered at 0, and then we did sine of maybe like 3x or 2x or something like that yesterday. So similar idea. Go ahead.
For f of 5, would it be negative 3, or does that go away?
Where? Here?
Like, yeah.
Well, okay, when you bring the negative 4 times negative 3, the two negatives cancel and become positive.
Okay, I got you.
That makes sense?
Yeah.
Okay, and so like on the next one, it would be negative 5 times 4 times 3 times 2. But it's going to alternate negative, positive because of that. Okay, other questions to there?
So just it kind of alternates because you're always multiplying by a negative.
Exactly. That's exactly right. Because you're always multiplying by a negative, this one alternates. Yep.
Okay.
Other questions so far? Okay, so we're going to go ahead and write out the expansion. So you don't have to, the stuff I'm writing in red is just kind of stuff we're thinking. You don't necessarily have to write. But when you put in k equals 0, and then k equals 1, and then k equals 2, here's what happens. So k equals 0, the entire top is f of 1, which is 0. That zeroes out the entire term. But then, okay, k equals 1 gets us the first derivative. So when we put f1 of 1, that's the first derivative, f prime of 1. So the whole top becomes 1 over 1 factorial times x minus 1 to the first. And then when I plug in k equals 2, I get f2 of 1. Well, that's off the list. That's negative 1. So negative 1 over 2 factorial, and then x minus 1 squared. We're just plugging in 2 for all these. Now we're going to plug in k equals 3, k equals 4. And again, you don't have to label these, just sometimes it's easier to think through what we're doing if we have that. So k equals 3 means third derivative at 1. That's off the list. That's 2 over 3 factorial, x minus 1 to the third. And then k equals 4, fourth derivative at 1. That's negative 3 times 2 over 4 factorial, x minus 1 to the fourth. And then k equals 5 is 4 times 3 times 2 over 5 factorial, x minus 1 to the fifth. And then that keeps going. That is a plus. And sorry, I'm kind of on the edge of my screen, but plus and so on from there. Any questions to here? Is everybody clear what we're doing there? Okay, so now you want to simplify down, but only if whatever you're simplifying simplifies consistently through the series, because we're trying to find patterns here. And so yesterday, like a lot of what we did is we had 0 terms that fell out, and here we only have one of those, but we can definitely drop this 0 term. The other thing, though, is that if you look at this 4 times 3 times 2, and then you look at 5 factorial, what happens there is that you get 4 times 3 times 2 over 5 factorial is the same thing as 4 times 3 times 2 over 5 times 4 times 3 times 2. And, you know, technically times 1, but so is the top. And so then you can cancel the 4, 3, 2, 1 with the 4, 3, 2, 1. And so you actually get just 1/5 for that term on k equals 5. And then we can do the same thing here. So if I have 3 times 2 over 4 factorial, or if I have negative 3 times 2 over 4 factorial, that's negative 3 times 2 times 1 over 4 times 3 times 2 times 1. And the 3, 2, 1 cancel, so you get negative 1/4. So it still alternates, but the factorials cancel out, and you're left over with just one number in the bottom. You're just left with that largest factor in the bottom. And so you can simplify these last couple this way. So this last one we can write as 1 over 5, but not 5 factorial. And then this one can be negative 1 over 4 times x minus 1 to the fourth. Does everybody see how that works out on those? Would be good. Okay, so the same thing can happen here. This is 3 times 2 times 1. Well, the 2 times 1 can cancel with the 2, so we get 1/3 times x minus 1 to the third. And then, okay, you can think of this as canceling or whatever, but 2 factorial is 2. So you get the same pattern. And then this one simplifies more. But to be consistent with the rest of the series, let's just leave it as 1 over 1. We can drop the factorial because 1 factorial is 1. And then we want it to be consistent with what's going on down here. Does everybody follow what happened there? Any questions to there? Okay, so now we're going to try to come up with sigma notation for this. And we can start wherever we want, but it probably makes sense to just start at 1 rather than 0. You could start at 0, but may as well start at 1 because we didn't lose any terms except this k equals 0 term. So take a minute and see if you can come up with the formula for this, because sometimes that's the trickiest part of this. But you need to come up with a formula where if I like plug in k equals 4, I get that entire term. Or if I plug in k equals 5, I get this entire term, and so on. And so take a second to try that and then check with me in just a few seconds. Okay, so a couple things going on. So the top actually alternates 1, -1, 1, -1. Whoops, let's do this in blue. So it alternates 1, -1, 1, -1. Yesterday we kind of looked at one where it was -1 to the k and -1 to the k plus 1. Here we want -1 to the k plus 1 or k minus 1, either way works, because we need k equals 1 to give us a positive 1. We need k equals 2 to give us a -1. So if I plug in 1, I get -1 squared, which is 1. If I plug in 2, I get -1 to the third, which is -1. If I plug in 3, I get -1 to the fourth, which is positive 1. So that's what we want. The bottom is just k, and then we get x minus 1 to the k. And so this is probably the easiest way to write this. And so we'll actually go with that as our Taylor series for natural log x. Any questions on that? Is that what we're getting? Okay. All right, so I didn't ask for the interval and radius of convergence. It turns out that the radius of convergence is 1. It goes from 0 to 2. We'd have to double check, but I believe that 2 is included. 2 is included. 0 is definitely not included. So if you did find the interval and radius of convergence, that would go from 0 to 2 with a bracket, and the radius is 1. The center there is 1. So the distance from 1 to 2 is 1. The distance from 1 to 0 is 1. So the radius is 1. You would get that using the ratio test like we were doing a few videos ago or a few days ago in class. All right, any questions on that example? Everybody good doing that? So I said power series. This could also be described as a Taylor series centered at 1. This one would not be described as a Maclaurin series because Maclaurin means the center is 0. But other than that, Maclaurin series is basically the same idea. But Maclaurin here would not make any sense because it's centered at 0. All right. All right, so we're going to do one more example like this. It's actually easier than this. And then we're going to do something else where we can go from the a series we've already got. So we're going to derive the Maclaurin series for f of x equals e to the x. And so again, Maclaurin series, Taylor series, power series in this context are all more or less the same thing. Maclaurin series means that the center has to be 0. But we could say power series here. We could say Taylor series centered at 0. All of that would be basically the same. So we're going to say, okay, well, e to the x is equal to the sum k equals 0 to infinity fk of the center, but the center is 0, over k factorial times x minus 0 to the k. So we actually don't need the parentheses. X minus 0 is just x, so x to the k. And so we're again going to try to find a pattern for the top. So we'll make a list of the function and a bunch of its derivatives. And again, you make the list until there's a clear pattern. So first derivative is e to the x. Second derivative is e to the x. Third derivative is e to the x, and pattern's pretty clear at this stage. So we probably don't need to go any further, but if you want to go further, you can. The derivative is obviously just e to the x every time. You then plug in the center. E to the 0 is 1. So then all of these are 1. So second derivative, first derivative, second derivative, e to the 0, 1. Third derivative, e to the 0 is 1. And so that continues. And so there's an easy pattern. Like I said, this is probably the easiest example. A lot of times people will do this one first. I usually do this last because there's almost, this one's almost too easy and you don't see what's going on if we haven't gone through the more complicated examples, but this one's much easier to deal with. So now if I go with k equals 0, k equals 0 gets me 1 over 0 factorial x to the 0. K equals 1 gets me 1 over 1 factorial x to the first. K equals 2 is 1 over 2 factorial x squared. K equals 3 gets me 1 over 3 factorial x to the third, and so on. Any questions to there? Okay, so now you take a minute and see if you can get anything to simplify. And if nothing simplifies, then go ahead and write it in sigma notation. So either way, take a minute to try to get it in sigma notation and then check with me in just a few. Okay, so you could simplify these first two terms a good bit, but it's not consistent with what's going on the rest of the series. So to do sigma notation is probably easier not to simplify those, or it's definitely easier not to simplify those. And so if we do the sigma notation, we get this. It's the sum k equals 0 to infinity. The numerator is always 1. The bottom is always k factorial, and the x part is always x to the k power. So we get that Maclaurin series or Taylor series for e to the x. Any questions on that problem?
Only one. Since the 1 is the top, could you just do x to the k over k factorial?
Sure.
Or is there a reason to have it separated?
No, there's no reason why I separated. So you can definitely write it as x to the k over k factorial. And actually, we're going to see a problem where it's useful that you notice that. So
Okay.
those are exactly the same thing. Does that make sense to everybody? Okay. Other questions? Okay, and again, we're not going to go through the ratio test, but if you were to do the ratio test on this, you would get 0 for that, no matter what x is. So the interval of convergence is negative infinity to infinity, and then that makes the radius of convergence infinity. Again, we haven't shown that. You would show that using the ratio test. Okay, so we're going to go through a few problems where we can use known Taylor series or known series in order to get series for more complicated functions. So 3 series that we know now are that e to the x is equal to 1 over k factorial x to the k on negative infinity to infinity. And then yesterday we derived that cosine x is equal to the sum k equals 0 to infinity of 1 over 2k factorial x to the 2k and sine of x is equal to the sum k equals 0 to infinity of 1 over 2k plus 1. And this one's in the homework. We didn't do this one in class. Centered at 0. We did it somewhere else. But those are 3 series, and the book kind of summarizes some more. It summarizes inverse tangent and probably natural log x, which we did, but we're going to use these 3 in particular. Normally, your all's test is open book, so you can write these down, but normally I would want you to memorize these 3. If you notice, and we're not going to go into it in a lot of detail, if you take differential equations, which a lot of people call Calc 4, hopefully you'll see this. But there is a weird connection here. This is all the odd factorials and all the even factorials and x to all the even powers. This is all the odd factorials and x to all the odd powers. And this is all of them. And so there's some weird connection between cosine x, sine x, and e to the x that happens here. And so anyway, that's an odd thing to notice. But that is something that's true here. You get some weird connections between those, and that is something interesting to look at beyond what we're going to cover here. But anyway, those 3 can be used to find more complicated series. So let's use a known series to find a series for f.
I didn't get that.
Oh,
Could you try again?
sorry, I'm talking to her, and I'm
Not sure I understand.
yeah. All right. Sorry about that, you guys. All right. To find a series for f of x. And so number 1 is going to be f of x equals 5x squared e to the 3x to the 7th. All right, and so we're going to use the series that we know in order to get this one. And so this is something that looks a lot harder than it is. But the way we do this problem is we think, okay, well, we know e to the x is equal to the sum k equals 0 to infinity of 1 over k factorial x to the k. And the idea is that this x corresponds to this. So then if the exponent is 3x to the 7th, then f of x is equal to 5x squared times, so instead of e to the 3x to the 7th, e to the x is this with x there, e to the 3x to the 7th is this with 3x to the 7th there. So you sub in 3x to the 7th in place of x. Okay, so e does not go in this at all. E to this power is equal to this sum with 3x to the 7th replaced or put in place of that x. Does that everybody see what happened there? 5x squared stays there for now. E to this power becomes this series with the 3x to the 7th replacing the x. Okay, now we're going to simplify this in 2 steps. So we're going to first raise everything in the parentheses to the k power. And so we're going to leave 1 over k factorial, and we're going to make it 3 to the k times x to the 7k. So we raise each part to the k. And then actually, I'm going to take one additional step. I'm going to put the 3 to the k on the top of that fraction. Normally, I would skip what I just wrote. And so I would recommend, and I think it makes it easier, if you put all the stuff without x, all the coefficient part at the beginning and all the x stuff at the end, it makes it easier on these problems. And now we're going to put the 5x squared in. So the 5 we're going to multiply in with the coefficient. It goes on the top. So we get 5 times 3 to the k over k factorial. And then the x squared times x to the 7k, we add the exponents. And so that's x to the 7k plus 2. Just be careful, it's not 9k. You can't like combine those, but it is 2 plus 7k. So that is the new power of x. So this is the power series for 5x squared e to the 7x, or 3x to the 7th. Does that make sense, everybody? Any questions on that? Okay. And so let's let you guys try one. So you guys try real quick. Number 2, f of x is, we'll say 3x cosine of negative 5x to the 4th. Okay, so I'll give you a few seconds. Let's try that, and then we'll check it together in just a minute. I'll go ahead and write the cosine series that we know. So cosine x is the sum k equals 0 to infinity of negative 1 to the k over 2k factorial x to the 2k. All right, so to start this, we leave the 3x outside, but instead of cosine of negative 5x to the 4th, we sub in negative 5x to the 4th into the known series for cosine. Okay, my bad. And now we simplify in a couple of steps. So we get 3x, and then we get negative 1 to the k over 2k factorial, but then some more stuff comes into this coefficient. We get negative 1 to the 2k times 5 to the 2k on the top, and then x to the 8k at the end. Does that algebra make sense to everybody? All right. Now, negative 1 to the 2k actually cancels because 2k is always even. So negative 1 to the 2k is 1, so we can get rid of that. Now we're going to distribute the 3x in. So the 3 goes to the top of the fraction. We get negative 1 to the k, 5 to the 2k times 3 over 2k factorial. And then x times x times x to the 8k is x to the 8k plus 1, because this is understood to be x to the first, and you add the exponents. Questions on that? So this is the series for 3x cosine of negative 5x to the 4th. Okay, so that gives us a way to do some antiderivatives that we've not been able to do before.
Actually, I do have one question.
Sure. What's your question?
Why do you keep the negative 1 to the k and the 5 to the 2k separate when you can multiply it and get negative 5 to the 3k?
Well, you can't get negative 5 to the 3k because the bases are two different things. So
right.
You can't combine in that way. If they have the same exponent, if they were both to the k, you could do that. So you could actually make it like negative, you're fine, but you could make it negative 25 to the k. But normally we separate out negative 1 to the k because that's like the alternating term. Does that make sense? Okay, yeah. No problem. Other questions? Okay, so the third problem we're going to do, or next problem we're going to do, evaluate the integral of e to the x squared dx. And so this is an integral a while ago that I think we mentioned that you actually can't do using any standard integration technique. So like U substitution doesn't work, parts doesn't work, trig sub, partial fractions, none of that stuff works. You can actually prove beyond basic calculus, but it has been proved that you cannot do this using what's called elementary functions, meaning you can't get a normal looking antiderivative for this, but we can get an antiderivative as a series for this. So we know that e to the x is the same thing as 1 over k factorial x to the k from k equals 0 to infinity. And you know what, real quick, I want to make sure that is what I wrote up here. And what was it when we did that summary? Yeah, okay, I did. I thought for a second, this is what I did wrong. Back up here, these are negative 1 to the k over these, which is what I've been using. But go correct that in your notes if you didn't get it before, my bad. Those are negative 1 to the k over 2k factorial, negative 1 to the k over 2k plus 1 factorial. Go correct that if you didn't make it. Though that's definitely what we had yesterday, and that's what the answer is in the homework. My bad, just forgot to put that earlier. I knew there was something up here that I'd done wrong. Could not remember what. All right, just take a minute, fix that. Sorry about that, you guys. And now let's go down here. And anyway, so e to the x is positive 1 over k factorial x to the k. And so e to the x squared then is the sum k equals 0 to infinity of 1 over k factorial times x squared to the k dx. And so again, this is something that looks insanely hard, but it turns out is not that bad. We know that if e to the x is equal to this series with x there, then e to the x squared is this series with x squared there. So I can simplify this real quick. And make it 1 over k factorial x to the 2k dx. And then we learned last week that this is actually easy to do. You just do the power rule on this. So you do what's called term by term anti-differentiation, and you add 1 to the power. Well, 2k plus 1 is just 2k plus 1, not like 3k or anything, but you can make it 2k plus 1. And so we get a constant plus the sum k equals 0 to infinity of 1 over k factorial times 2k plus 1 x to the 2k plus 1. And that's not like a normal looking antiderivative, but that's actually the best antiderivative we can get for e to the x squared. So it's equal to this. The interval of convergence is actually negative infinity to infinity. The theorem we talked about last week that lets us do integrals that way says that when you do the integral or antiderivative, the radius of convergence does not change. Well, the radius of convergence here is negative infinity to infinity for this one. So it is for this one. And then when you take the integral, the radius of convergence stays as infinity. So the interval is negative infinity to infinity. But this is how you do that antiderivative. And then it's probably not hard to see that there's problems like this. This one might be one that you can't do. In fact, it's pretty likely that you can't do this. So if you wanted to take the integral of this, we would use this series and take the antiderivative that way. All right. Any questions on this? Okay, I want to look at 2 more kind of weird problems and then we'll be done for the day. So number 4, maybe we might do, and we'll just do 2. So let's find the sum. So find the sum of the series k equals 0 to infinity, 3 to the k over k factorial. And so the only series that we have learned to find the sum of at this point are geometric and telescoping. And it's pretty quick to notice it's for sure not telescoping and it's not geometric because of that k factorial. So then there has to be another way to do it. Well, if you notice, this looks a lot like this. And so given that it's exactly this with a 3 in place of x, The sum of this is e to the third power. But you have to notice that it's in this form. Does that make sense to everybody? Any questions? All right. And we are going to do 2 more examples. I'm sorry, guys. We'll do 2 more. They'll be very quick, but 2 more. So find the sum. All right. So we have to be a little bit careful here. But why is the answer to this not just e to the 4th? It's a little
K
more.
starts at 2.
Yeah, because k starts at 2. So okay, so what happens is if it started at 0, it would be e to the 4th. So the sum k equals 0 to infinity would be e to the 4th, but then we subtract out k equals 0 and k equals 1 because those aren't here. So k equals 0 is 4 to the 0 over 0 factorial. K equals 1 is 4 to the 1 over 1 factorial. So it's e to the 4th minus the k equals 0 term and minus the k equals 1 term. We want the k equals 2 term, but we don't want the 0 and 1. Does that make sense? Everybody clear? And then, okay, 4 to the 0 over 0 factorial. 0 factorial is 1. So this is 1. 4 over 1 is 4. So this is e to the 4th minus 5. And that's the simplest we can get. But the sum of that series is e to the 4th minus 5. All right, change my mind because I'll let you guys do this on the homework and on some practice stuff after break. But you could do the same thing for series that look like sine or cosine or natural log or something like that. And you just have to notice it's equal to the known series. Okay, that is it for today. Please take a break over Thanksgiving. So don't work. If you want to work a little bit this afternoon just to practice this, that's completely fine. This is on Power Series 3 on the worksheets, but there will not be any required homework on this until after break. Please do not work on calculus over Thanksgiving break. Just take a break until the Monday after. When we get back that Monday, we will need you guys working on stuff pretty much every day. We'll have a week to get ready for the final. There is a little bit of new material after break on parametric equations and polar coordinates, but there's no more on Power Series. So we're done talking about those. You guys have a great Thanksgiving. Thanks for coming today. And I will see you guys in a little less than a week. Have a good break.